It turns out some triple integrals, and I mean fairly obviously that triple integrals can get complicated for sure. Turns out that some triple integrals, depending on your region that you're triple integrating over, are better in to do in what are called cylindrical coordinates. Now, the cylindrical coordinates, what that is, it's the three-dimensional version of polar coordinates. And so, just like, you know, we talked about double integrals, sometimes double integrals are easier in polar coordinates. Not always, but sometimes they are. Well, same thing holds for triple integrals. Sometimes it's easier in this three-dimensional polar coordinates to do the triple integral in that. And by the name, you probably would suspect which ones. Well, it would be triple integrals that involve cylinders. Paraboloids also, you know, the three-dimensional parabola. It's another, but anyway, we'll get more on that in just a second. But anyway, so let's talk about cylindrical coordinates just to kind of get the feel for them. Three-dimensional polar coordinates is what. So we're not going to start with a triple integral yet until we figure out what cylindrical coordinates are. Yeah, so cylindrical coordinates, you've got r, and you've got theta, and just like polar coordinates. But it's three dimensions, so you need a third coordinate. Luckily, the third coordinate is z, okay? So that's nice. There was anything nice about it. So yeah, you got r theta, but then you have that third dimension. They just use the z for it. So instead of naming a point in x, y, z, it's r, theta, and z. And so the good thing is, guess what x and y are equivalent to? So if I've got x, y, z, and I want to convert that to the r theta z, guess what x and y are going to be? Or how do we get the r and theta? Well, it's the same as before. You know, r is the square root of x squared plus y squared. And then theta, remember how we got theta out of it? We got the x, y, z. So if we had x, y, how do we get theta? Use the tangent inverse. Usually, this is how they usually write it. Tangent of theta equals y over x, because you can't, sometimes the tangent inverse gives you more like a reference angle. Sometimes you have to say, well, I need to add 180 degrees or pi units to that, you know what I'm saying? So that's good news. The way you convert from x, y, z to r, theta, z cylindrical, same way we did with polar to get the r and the theta, and then vice versa to get, if we've got r, theta, z, how do we get x, y, z? Well, x is r. So if you got r, theta, z, how do you get the x, y, z? Well, you got the z. I mean, z is z, so you got the z. That's the same thing here. But how do you get the x, y if you got the r theta? Well, x is r cosine theta, y is r sine theta. So that's good news. It's convert from Cartesian to polar, use the same thing. I mean cylindrical, use the same thing you did for polar. To go from cylindrical to Cartesian, same thing you did for polar. So that's pretty sweet. Now, just to kind of show you how it works, let me just give you a typical r theta z point. All right, so let's say I've got this point and it's out here wherever in the first octant or whatever, doesn't matter, but your R and theta are the same thing. Your R is, let's see, the one I'm going to do here is still the length in the XY plane, and theta is the angle from the positive x-axis. So that's R and that's theta in the XY plane. So that, it's all still the same. The only thing is we're adding that third part, and that is the z. So z is z. So you go up from whatever that point in the XY plane is up to z units, down or up, whatever the case may be. And that's your R theta z. So theta and R are still in the XY plane. That's what we're basically saying here. It's the same thing we've always done. It's just that now we're giving it height, if you will, or down. Okay. So let's plot 3 2/3 2. R theta z. Well, you know, you got it. Visualization type thing. So, yeah, your angle is 2 pi over 3, so that actually, I mean, if you think about it in just the XY plane here first, maybe it'd be helpful, but the XY plane, where does that put theta at? Which quadrant? 2 pi over 3. Way I look at it, that's 2/3 pi, so I haven't quite reached pi, it's 2/3 of the pi. And it's past pi over 2, so wouldn't that be somewhere along here? And then R equals 3, so 3 units out there. All right, so what that's telling me is it's going past the y-axis. So over here, this is the positive x-axis, so I go past my y-axis there. And then R extends out 1, 2, 3 units. So in my XY plane, I'm over here in this part. Now I need to go up 2 units from that, so I'm back into the board really, and then up 2 units for Z. So it is kind of hard to draw that in 2 dimensions, but hopefully you get the idea. It is into the board a little bit and then up 2 units. Somewhere in that vicinity. Maybe putting a little square out there. Well, that's not very straight line. Anyway. All right, what would they call it rectangular instead of Cartesian, but 3, 2 pi over 3, 2, what's that in rectangular coordinates, Cartesian? X, Y, Z. That works. Well, that's again what we said. Same things we've always done. Z is Z, so that's easy. Z equals 2. The X is our cosine theta, so that would be, in this case, 3 times cosine of 2 pi over 3. We should plug it in, but let's see. Doing a lot of reviewing here. All right, 2 pi over 3, that's it's in the second quadrant, so it is negative. Then yeah, so then cosine of pi over 3, is that square 3 over 2? No, sorry, 1/2. pi over 6 is, cosine of pi over 6 is square root. Cosine of pi over 3 is negative 3. It's money. Plug in your calculator. It'll give it to you, I guess, but sometimes remember these things. All right, so then our sine theta is y. That'll be 3 times sine of 2 pi over 3. Well, again, quadrant 2, so we're in positive y territory there. And then reference angle is pi over 3, which is square root of 3 over 2 is the sine. So it would be 3 square root of 3 over 2. So x, y, z, you're going to have negative 3 halves, 3 square root of 3 over 2 be the y, and then z is z, so z is 2. So not too bad, huh? Let's do a couple of them going the other direction. Rectangular, cylindrical. Then we'll maybe tackle some triple integral. Be triple integral. Anyway, all right. So find cylindrical coordinates for number 1, 6, -5, and 3. So that's my x, y, z. I want the r, theta, z, right? R is easy, Pythagorean theorem kind of thing, right? R is just the square root of x squared plus y squared. So it'd be 36 plus 25, 41? No, 60. Square root of 60. Easy. All right, then for theta, we have tangent of theta equals y over x. Well, that would be tangent of theta equals y, -5 over 6. So easy enough to say, well, theta then, but here's the thing. When you do the inverse tangent, that only goes in a specific range, doesn't it? Inverse tangent is between negative pi over 2 and positive pi over 2, which basically is quadrant 4 to quadrant 1. It's somewhere in this range here. That may not be, so you are going to use the inverse tangent, but that angle that you get from that may not be the angle really that you want. Because you may have a quadrant 2 or quadrant 3 angle, and you have to. But in this case, so what do you do? Well, if you just plot the xy point, the point in xy terms, so you got x is 6, y is -5. Hey, we're in good shape here because we are in quadrant 4. So that tangent inverse is going to be, you see what I'm saying? Theta is tangent inverse -2. We can say that. In this case, it's fine because that's going to give us a quadrant 4 angle. You know what I'm saying? And they probably, in that case, would just leave it that way. I mean, if you want to, that's approximately, that I thought I wrote down, 0.69, negative 0.69 radians, degrees, you get it in degrees, but that's probably the way they would write it. So there's my R, there's my theta, got my Z, so there's the answer. Square root of 61, tangent inverse, -5/6, and then Z is 3. So that wasn't too bad. Well, let's look at this. What about number 2, -3, -2, -1? the r theta z for that one. R's not that bad. Z's not that bad. Z's given, so definitely not bad. What would R be here? 9 plus 4 square rooted, square root of 13. Yeah, so R and Z, no sweat. Theta is a little trickier sometimes in this case. It is the tricky one here. But we know the tangent of theta is y over x, so the -2 over -3, 2/3. If I do the inverse tangent of 2/3, note here what that gives me. It approximately gives me, I didn't write it down.
1.588
0.588
radians.
radians, which is what in degrees? I think I'm
33.69 degrees.
It's about 33.7 degrees. Okay, here's my point. That's not the angle I want here because look, in the XY plane here, I'm not in quadrant 1. I'm in quadrant 2. So this angle here is not 33.7 degrees.
Wait, is
my
it
point.
quadrant 3? Because it's -3, -2.
Oh, sorry. Yeah,
Okay.
I did positive 2, didn't I? Same,
Same thing. Yeah.
same difference. Except when we go find the angle because, all right, so yeah, we're definitely not 33.7 degrees because that'd be in quadrant 1. So what do I need to do? Well, I need to take this angle pi and then add in this right here is 33.7 or the tangent inverse of 2/3. So it's pi plus 180 plus 33. So here's how they'd write it. So theta actually is pi plus tangent inverse 2/3. You with me? That's what theta is going to be. So really what this gives me is a reference angle. Call it. That's what I call it when I did trig stuff. So it doesn't necessarily give me theta, but it gives me the reference angle for theta. And then I can, sometimes the reference angle is the angle, that's fine. Or maybe I should, anyway, you know what I'm saying. Okay. So the answer, what's the answer? R is square root of 13. Theta is pi plus tangent inverse 2/3 is the exact value around it. I think they do exact. What would it be? 3.14 plus 0.559 if you rounded it. But it is Z to Z, so.
Some nice round numbers here.
Do I like the nice round numbers?
Oh, yeah.
Sometimes they're more round than others, aren't they? They're round and around.